In this lesson, we'll start with a refresher on network basics. A network is a collection of devices and systems, connected to each other and able to communicate with each other. It could be computers, servers, smartphones, routers, and more. A network can be as big as the internet, or as small as two PCs who share the same printer. Among the components that can be found, there are PCs. These are end devices, which are found at the ends or tips of the network. They're capable of sending and receiving data. There are interconnections. These are the components that ensure that data can travel from one device to another. These interconnections include network card. They're the ones that translate your computer's data into a network-readable format. Media. These are network cables or wireless protocols. These are network cables or wireless protocols like Wi-Fi. And connectors. This is the plug that plugs into the network card. Going back to the components. There are switches. These are devices that provide a network connection to end devices like PCs. And there are routers. They serve the role of interconnecting networks and choosing the best path for each destination network. On this network diagram, we see a computer connected to a switch. On the top of the diagram, you see the FA01 notation, which means that the computer is connected to the Fast Ethernet 0-1 interface on the side of the switch. The 0 is the controller's number, and the 1 is the port number. Our switch is connected to a router using its Fast Ethernet 020, and the bottom router has an internet connection using a serial interface. We use networks on a daily basis, including for applications, like sending data between computers, browsing the web, or sharing files. Resources, like shared printers or home security cameras. Storage, for example, an NAS, Network Attached Storage Device, which is a hard drive that's made available on its network or through the internet. Today, many people use them at home to share files, videos, and images between computers. Backup, a central backup server that all the computers on the network send their important data to back up. And VoIP, which means Voice over IP. VoIP is being used more and more around the world, and it'll eventually replace analog telephony. We all use everyday applications, which we can divide into three categories. There are batch applications. This can be file transfer with FTP or TFTP. It can also be an HTTP download from the web or a backup at night. There is no human interaction, and high bandwidth is important, but not critical. A batch app is something you let spin and easily forget because no one is waiting for an answer to take the next step. Whether it takes 1 hour or several hours, it doesn't matter. FTP, or File Transfer Protocol, is used to transfer files between a client and a server. For example, web developers might use it to upload new pages to their site. It was often used in the past to download software, but has been largely replaced by HTTP as the web became faster and more secure. TFTP, which means Trivial File Transfer Protocol, is like a stripped version of FTP, and is sometimes used to copy files between routers or Cisco switches. The second category is for interactive apps. This is an application that needs human interaction to take the next step. Here, someone is waiting for an answer. The response time or the delay is therefore important. As an example of an interactive application, you could take two users chatting on Facebook Messenger or iMessage. If users have to wait 1 minute between each message, it can be quite painful. That's why low delay is important. And the third category is real-time applications. These applications also involve human-to-human interaction. For example, live video conferencing. Here, end-to-end response time is even more important. Imagine you're talking to someone on the phone using voice over IP, and you have to wait 2 seconds before hearing the other person's response. It can quickly become very annoying to keep talking. Anything above a 300 millisecond delay, about 1/3 of a second, looks more like a walkie-talkie conversation than anything else. Latency is therefore critical when using voice over IP or live video conferencing. Even a delay of more than 150 milliseconds is noticeable. That's 1/8 of a second. In networks, we have 2 types of topologies that can be divided into 2 categories: physical topologies and logical topologies. There is a big difference between the 2. Physical topology is what the network looks like and also how all cables and devices are connected to it. And logical topology is the path that data signals take through the physical topology. Among the physical topologies, there's bus topology. The first networks were made using coaxial cables. It was a single long cable and each device was connected to it. At the end of the cable, you had to place a terminator. If the cable broke, the whole network went down. There's ring topology. Here, all the computers and network devices are connected to the same cable, and the last 2 devices are connected to each other to form a ring. If the cable breaks, the entire network will still be down. There's also a dual ring configuration, which is used for redundancy. That is, if the cable is damaged, the network will use the second cable to stay online. And then we have the star topology. Here, all the terminals are connected to a central device, creating a star shape. That's what we use most often in LANs. That is, the computers are all connected to a switch. The physical connections used are UTP cables, better known as RJ45. In this topology, if the switch breaks down, all the devices connected to it will lose their connectivity to each other. Now let's see another example of topology using a computer with several sites in different cities in America. In this example, each router is connected to all other routers. This will be a very resistant topology in the event of a breakdown. If a site fails, it won't affect any of the other sites. The only drawback to this configuration is very expensive to set up, because we need several links between the sites, and therefore several physical interfaces on each router. This is what we call a full mesh topology. Another option is to ensure that only the important sites have connections to all other sites, as in this example. Here you can see that the Philadelphia router has a direct connection with the other routers. Manhattan is only connected to Philadelphia, and Los Angeles has a connection to Philadelphia and San Francisco. This topology is a trade-off between failure tolerance and cost. In the past, network development was chaotic. Each supplier had its own proprietary solution. The problem with this was that one supplier's solution was not compatible with that of another supplier. This is where the OSI model was born. The model is composed of several layers, and the idea is that a hardware supplier can design the network layer, and other vendors can develop the application layer on top of it. An open model makes it easy to build networks that are compatible with each other. The International Standards Organization, ISO, researched different network models and published the OSI model in 1984. Nowadays, most vendors build networks based on the OSI model, and as a result, their hardware is compatible with each other. But the OSI model isn't just a model to make networks compatible. It's also one of the best ways to teach people how the network works. Let's see how the 7 layers work, starting from the bottom. The physical layer. This contains elements such as voltage levels, synchronization, speeds, physical connectors, etc. The physical layer includes everything you can touch. The data link layer ensures that the data is properly formatted. That's where Ethernet lives. MAC addresses and Ethernet frames can be found on the data link layer. The network layer supports connectivity and path selection or routing. This is where IP lives. Each network device needs a unique address on the network, and each version of IP used today, IPv4 and IPv6, has its own addressing system. The transport layer breaks data into packets to be sent from one host to another. For example, when you download any type of file on the internet, be it a PDF or a video, the file will be transported to your computer in segments. The P, Transmission Control Protocol, and UDP, User Datagram Protocol, live. TCP is a reliable data transport protocol, while UDP is not. These bottom 4 layers we've just seen are important for networking. The top 3 layers, which we're about to see, are used for applications. The session layer supports the establishment, management, and termination of sessions between 2 hosts. When you browse a website, you're not the only user of the web server that hosts that site. The server needs to be able to trace all the different sessions or all the interactions it's having with other visitors. The presentation layer ensures that the information is readable by the application layer by formatting and structuring the data. And the application layer includes all the applications you use, for example, email, web browser, FTP, and many others. There are many mnemonic phrases to remember the order of the OSI layers. For example, from bottom to top, please do not throw sausage pizza away. Or from top to bottom, all people seem to need data processing. With a little online research, you can find other funny mnemonic phrases. Keep in mind that it's impossible to go directly from the application layer to the network layer. You always have to go through all the layers to send data over the network. Now let's take a real example of data transmission. At layer 7, you're sitting behind your computer and want to download files from a web server. You start your browser and type the URL of your favorite site, asking for the page you want. So you're using the HTTP protocol, which resides on the application layer. The presentation layer structures this information into a certain format. The session layer makes sure to separate all the different sessions. Depending on the application, it will either use TCP for reliable transport or UDP for unreliable transport. In this case, as you want to be sure that the web page arrives fully intact on your computer, it will be TCP. At layer 3, your computer builds an IP packet, which contains all the data from the application, presentation, and session layers. It will specify the transport protocol to use. This package will also contain the source and destination IP address. The source address will be your computer's address, and the destination IP address will be the web server's. In layer 2, the IP package is placed in an Ethernet frame, which includes your computer's source MAC address and the web server's destination MAC address. And finally, at layer 1, everything is converted into bits and sent to the cable using electrical signals. It's important to know the purpose of each layer of the OSI model. Let's take another example, sending a letter through the postal service. First, you write a letter. You put the letter in an envelope. You write your name and the recipient's name on the envelope. Then you put the envelope in the mailbox. The contents of the mailbox will be sent to the post office. Then your envelope will be delivered to the recipient. And finally, your recipient will open the envelope and read what's inside. If you put your letter directly in the mailbox without writing the recipient's address, it won't get delivered. A network works the same way. Moving from the application layer all the way to the physical layer is what we call encapsulation, and the transition from the physical layer back to the application layer is called decapsulation. In peer-to-peer communication, each layer encapsulates the data in packets of information. The generic name for these packets is PDU, which stands for Protocol Data Unit. But PDUs are known by different names on each different layer. At the transport layer, the PDUs are called segments. In this case, we'll talk about TCP segments. At the network layer, the PDUs are called packets, so we'll talk about IP packets. And in the data link layer, the PDUs are called frames, so we'll talk about Ethernet frames. In addition to the OSI model, another organization has created a similar model that's never become popular. But for your CCNA, you'll need to know what it looks like. It's called the TCP IP battery, and it's very similar, except that some layers are combined and have different names. As you can see, the TCP IP battery combines the top 3 layers into the application layer. The network layer is called the internet layer, and the bottom 2 layers are combined into the network access.